Dear students, welcome to this course on electrical distribution system analysis. Myself Dr. Ganesh Kumbar. I am working as assistant professor in the Department of Electrical Engineering, IIT Roorkee. This course is specifically designed as an elective course for the students of undergraduate, postgraduates and PhD who are working in the area of distribution system and smart grid. This course will also be useful to the utility engineers who are working in the distribution sector. The basic power system courses like power system analysis, power transmission and distribution, power system engineering, switchgear and protection are the basic prerequisite courses for this particular course. In this particular first lecture, we will see following topics. So, content of my today's lecture will be introduction to the electrical distribution system. So, I will introduce you to the electrical distribution system. Then we will see the structure of distribution system. Basically, distribution system is classified into two parts, that is primary distribution system and secondary distribution system. So, we will see the structure of this primary distribution system and secondary distribution system. Then we will see why distribution system analysis is required. So, you might have already studied the power system analysis. However, this distribution system analysis will be different from earlier power system analysis. So, we will try to find out what are these differences. Then we will see the motivation and objective of this particular course. Then we will see the course content, and then we will see the reference books required for this particular course. As we have studied in our undergraduate courses, the power system can be divided into three parts, that is generation, transmission and distribution. So, if you see this figure, generation is shown here, and then this is nothing but your transmission layer, and then this is nothing but your distribution part. Voltage level of the generation is around 11 kV to 25 kV. Now, this voltages which are 11 to 25 kV will be stepped up to the transmission level, that is 220 kV to 765 kV, which are the voltages for bulk transmission network. Then they will be stepped down to the sub transmission level. The sub transmission level is 66 kV to 132 kV. Then it will be further stepped down to the distribution level. So, voltages at the distribution level are below 33 kV. Distribution level can be divided into two parts, that is primary distribution system and secondary distribution system. Primary distribution system will be having voltage level between 4 to 33 kV, and secondary distribution system will be having voltages, that is 400 volt 3 phase and 230 volt single phase. And if you see the structural difference between your transmission network and distribution network, transmission network is basically interconnected, means it will be forming some kind of loop here. But if you see the structure of your distribution system will be radial. So, it will be radial or weakly meshed. Basic goals of your distribution system are listed here. So, first goal, it should be efficient. It should be efficient means losses in the distribution should be less as possible. We should deliver the customer the quality power, means your voltage should not contain any harmonics, it should not contain any sags, swells or flickers. Then we should provide a customer reliable power. Power should be cheap to the customer, so it should be economical, and it should be secure power to the customer. If you see the topological difference between your transmission and distribution network, as I told you earlier, your transmission network is basically interconnected. So, as shown in this figure, you can see that it is forming some kind of loop, means which is shown like this, or you can say there will be actually one bus will be connected to many other buses, which is forming the interconnected kind of or loop kind of system. This is basically done to increase the reliability of the system, because as we know all these generators are dispersed over wide distances, and whenever there is contingencies like few lines or few generators, if they go out of the system, there is possibility that system will become unbalanced. To avoid this stability issues into the system, we want actually system to be interconnected, or it is forming loop kind of structure. Whenever there is some lines or some generators are out, the power will be still available from alternate routes. Your distribution system will be radial one. Radial means it will not be forming any kind of loop, or it is kind of weakly meshed system. Weakly meshed means there will be only few loops, unlike in case of transmission system. So, transmission system is highly interconnected kind of system. The basic reasons to make the distribution system radial are as follows. First is, if you see the cost of the system, cost difference between interconnected system and this radial system will be very cheap, that is cost of the system will be very low. It is easier to protect, so protection system will be cheap as well as easy to protect, because you know that in this case if you see the radial system, the current will be actually having only one direction. So, whenever there is fault occurred at some location, so the current will be fed from only one direction to the fault. So, in that case your protection will become easier. Also, since the power is flowing from one direction, so voltage drop will be in one direction, that is why voltage control will also become easier. Finding the fault also will become easier, because power is flowing, fault current as well as power, they are flowing from one direction. It is also easier to control the power flows. Now, if you see the structure of your primary and secondary distribution system, which you have seen earlier, the primary distribution system basically consists of your 11 kV network. We also call it as HT level, high tension lines. It starts from your 33 to 11 kV substation, and it will be basically 3 phase 3 wire system. So, there will be 3 wires RYB at 11 kV level. This feeder will be basically connected to different substations, which are 11 kV by 400 volt substations. There will be many such substations will be connected to this feeder. We also provide power to bigger consumers like malls or big industrial consumers at 11 kV 3 phase level. So, there actually shown in figure, there is one bigger industrial consumer which is taking power at 11 kV level and at 3 phases. Similarly, there is one commercial consumer which is shown it here, which is 3 phase. If you see the secondary distribution system start with 11 kV by 400 volt substation, and it is basically 3 phase 4 wire system. So, there are 3 phases R, Y, B and one neutral phase. So, 3 phase 4 wire system. It will be providing power to the some big consumers as well as some domestic consumers like our houses. So, if you see here the factory which is little bit big consumer, we are providing the power to this big consumers at 3 phase levels, means all 3 phases are there with your neutral connection. And to our domestic consumers, we feed the power at single phase level. So, if you see this house, it is taking the power at R and N phase, which is single phase R. Then if you see this house, it is taking at power at Y and N phase, and this house is taking power from B and N phase. So, this is structure of your distribution system, which is secondary distribution system. Now, we will see transmission system analysis. So, basically in this particular slide we want to see what are the assumptions we have made during the transmission system analysis. So, we know that the transmission system is basically interconnected kind of system. So, your algorithm should be such that this interconnection or loop kind of structure it will take into account. Then we know that these transmission lines are basically transposed one. Transposed means these lines will be changed at different locations. So, every conductor of this line will be taking location of every other conductor. So, we know that transmission, these lines will be transposed lines. Then we know that actually loads are balanced one. Generally at transmission level loads are balanced. Then we know that X by R ratio of transmission system will be very high. Because of this X by R high ratio, decoupling is possible. Means your P and Q can be differently controlled. So, P can be controlled by just changing the angle delta, which is basically phase angle difference between voltages at sending and receiving end, and Q can be controlled by voltage magnitudes. So, as I told you, because of this decoupling effect, we can get decoupled kind of load flow algorithms. Then there are actually fewer components. As you know, only few components we need to model during the transmission system analysis. Those are basically reactors and your transformers, or maybe sometimes capacitor banks. Then, as you remember, during the modeling of transmission system load flow, we modeled it as a single phase equivalent network. Means lines as well as transformers will be modeled as single phase equivalents. Because of that, we are not considered any individual connections of the transformers. I mean, even if it is delta star or star star or delta delta transformer, we modeled it as a single phase equivalent of them. Then loads which we have modeled in transmission system, we have considered them constant power loads. Means voltage dependency of the load we are not considered. Because of that, at each iteration of load flow, your power is remaining constant. Means we are not changed our power values during load flow iterations. Then symmetrical component analysis was possible. So, we know that actually since lines are transposed, we get your because of transposition, we know that your self impedances of the line, they will be equal. So, self impedance of all the three phases, we know that it is, we make it equal to say ZS, 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 and mutual impedances between line also we make them equal. So, ZM, 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 they are equal. And we know that if you pre and post multiply this matrix by A inverse, which is symmetrical component transformation matrix, and A matrix, we if you multiply it to this impedance matrix, which is Zm, 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 and diagonal entries Zs, 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 we get only a diagonal matrix, that is Z0, Z1 and Z2. Meaning of this, your three network, that is zero sequence network, positive sequence network and negative sequence networks, they are decoupled from each other. Unlike this, if you go for distribution system analysis, distribution system network, as we discussed, it is radial or weakly meshed kind of network. So, because of this structure, we know that we can find out some algorithm which are simpler in nature than your transmission algorithm and specifically designed for your radial or weakly meshed kind of system. However, in case of distribution system, your loads are totally unbalanced loads, your lines are untransposed, your ratio of R by X will be higher, okay. Means since the ratio is higher, you cannot do the decoupling, means there will be actually voltage magnitude will also make effect on your power, as well as your delta will make effect on your Q, okay. So, delta will make effect on both, voltage will make effect on both of these quantities. Also, as compared to transmission network, size of distribution system will be very large, okay. When we are analyzing the transmission network, the number of buses which we are considering is around hundreds of buses, but in case of distribution system, the large distribution system I am talking about, it will be around thousands of buses. So, system size is very large. In distribution system, there are many components which are present, like there will be capacitors, there will be regulators, there will be distributed generation, there will be battery storage. Also, if you see the structure of your distribution network, there will be some line which are actually single phase line, some lines which are 3 phase lines, and some line which are actually 2 phase lines. Because of that, we cannot do single phase equivalent analysis in case of distribution system. So, we need 3 phase analysis for distribution system. Symmetrical component analysis is also not possible because there are untransposed lines. So, this 0 sequence, positive sequence and negative sequence networks will not be decoupled from each other. In this case, since we are considering full 3 phase modeling, your YY, Y delta or delta delta connections need to be actually modeled during the analysis of distribution system. Loads in a distribution system are basically voltage dependent. Because of this voltage dependency of the loads will change in each load flow iterations. So, that need to be considered while doing the load flow analysis. So, voltage dependency of the load needs to be taken into account. Distribution system analysis will need time series simulations. So, we need to calculate the load flow solution at different time steps, that is called as time series simulations. Also, nowadays many smart grid components are coming into picture, and these smart grid components will make your distribution system analysis little bit complicated, and those smart grid elements are controllable loads, distributed storage, battery storage, electrical vehicles and demand response activities designed by utilities. So, because of them your distribution system analysis is important. Now, we will see where this distribution system is required or where it is applicable or where it is used. So, as I told you, the basic analysis is load flow analysis and short circuit analysis. So, load flow analysis is required for taking various decisions during operational stage of the distribution system as well as design stage of the distribution system. So, during the operational stage like load balancing or reconfiguration of the distribution system, we need load flow analysis. During the design stage, while we are selecting a conductor size of the distribution conductors or transformer sizes, we need to know the load flow solution. Voltage regulation and tap operation during the operational stage, we need results from load flow analysis. Power loss reduction, we need load flow analysis. Then nowadays capacitor placement as well as DC placement, we need results from load flow analysis. or load flow will be basically will be used during these different types of analysis. Then short circuit analysis is required while doing the settings for protective relays or during the relay coordination in a distribution system. Also to calculate short circuit current in the upstream network. So, we need actually results from short circuit analysis during these design stages. Now, we will see what is the basic motivation and objectives for development of this particular course. As we know, most of the power system courses mostly focus on your transmission system analysis, and as we have seen in last 2-3 slides, there are many components which are different. The structure of distribution system is very different from your transmission system. We need to have separate algorithms or separate method for distribution system analysis. We also know that nowadays with incorporation of distributed generation, battery storage, controllable load, distribution system is no longer remaining passive in nature, means distribution system is becoming active because of this energy generation sources or energy storage sources which are present in your distribution system. Also, distribution system is considered to be weakest link in whole power system because it is most loss making component. So, almost we can say 60 to 70% losses which happen in distribution system. Also, if you observe last 3 decades, there is gradual development in computational power, there is gradual development in optimization algorithms. Nowadays, there are many sophisticated algorithms are available for the optimizations which can be used during the analysis purpose. So, because of that, this distribution system analysis is becoming very important for the researchers who are working in the area of distribution system and industry professionals who are working in distribution sector. These results which we obtained from distribution system analysis will be quite useful while making the decision during the operation as well as design stage of the distribution system. Therefore, main objectives of this particular course are to familiarize the students with distribution system components and their modeling. So, first part of this particular course we will see how to model different components of the distribution system, and in second part of the distribution system the objective is to familiarize the students with methods and algorithms of distribution system analysis. So, in this particular part we will introduce you various methods and algorithms which are very different from your transmission analysis algorithms for the distribution system analysis. So, based on these objectives, the main content of this course is divided into 4 chapters. Out of this first chapter is based on introduction to the distribution grid. So, basically in this particular chapter we will see the structure of distribution system substation layout, distribution feeder configurations, nature of loads, computation of transformer and feeder loadings, that is nothing but your load allocation. Then we will see various approximate methods which are available for distribution system analysis. There are some methods which are based on K factors, so we will study them. The main aim of approximate methods is to get the voltage drop and power loss calculation on uniformly distributed load over the feeder. Then we will see various geometrical load configurations. Then in third chapter we will see modeling of distribution system components. In this modeling, we will basically see modeling of single and three phase overhead lines and cables. Then we will see the modeling of voltage regulator, transformer, capacitor banks, loads, induction motors and distributed generators. In fourth chapter, we will see distribution system analysis. So, in this particular chapter, we will try to develop algorithms for load flow analysis and short circuit analysis, which can be used for single phase as well as three phase systems. So, based on this content, the references for this particular course are listed here. So, first is book by W.H. Cresting on distribution system modeling and analysis. So, to model the distribution system components, we will be referring this particular book. Then there is book by Salam and Malik, electrical distribution system. So, this will be used for introduction to the distribution system as well as during the short circuit analysis of distribution system. Then there is a book edited by Dr. B. Das on power distribution automation, and this book will basically used while developing your algorithm for load flows and short circuit analysis. Then there is a book by J.M. Gers on distribution system analysis and automation, and then there is one paper by Arit and Dugan, which is distribution system analysis and future smart grid. So, during your introduction section, we will be using this particular paper. Okay. Therefore, in this particular class, we have started with introduction to the distribution system. Then we have seen the structure of distribution system. Then we have seen motivations and objectives for this particular course. Then we have seen that course content of this particular course and references. Thank you.